All right, good morning, everybody. Another day, another freezing cold morning, right? Great semester to have an 8 a.m. class. Before we get started, I just wanted to give you a couple quick reminders and sort of summarize important details about the exam. Exam is on Wednesday, remember. We already talked a lot about the coverage. But if you weren't here at the beginning of class on Wednesday, there will be a formula sheet allowed, so 8.5 by 11 front and back. You're welcome to have that with you during the exam. And then calculators are allowed, of course, no cell phones, so if you use your cell phone as a calculator, find something else, please. And that's it. That's all you'll be allowed. I will provide you with tables and anything that you'll need as far as that goes. But no other materials, closed book, closed note otherwise. And then I sent out an email maybe Wednesday about some extra review opportunities I'm going to do. If you haven't already noticed, there's like a practice exam type of thing on Carmen, and we'll take an hour and a half on Monday evening to go over that in Calkins Hall 232. If you can't make it to that, or if you have more individual questions, I'll also be holding extra office hours actually in my office, so not in the tutor room, in my office, which is Calkins 304C, for the few hours before that. And if neither of those times works well in your schedule, just let me know and we can try to set something else up other than that. Any questions you guys have on the exam or anything? Yeah.
This is maybe not really too relevant. The calculator says binomial PDF, and I always thought it was PDF.
Oh, yeah. Yeah, so the calculator, if you use your calculator, it often will, or it does say binomial PDF. That's the same thing as the binomial PMF. So they're abusing that notation, I guess. I don't know why they did it that way. Maybe just to keep it consistent. I'm not sure. All good otherwise? I do have your homework 2 to hand back. I'll do that at the end of class. And also don't forget you do have a homework assignment due on Monday. Oh, I would say, obviously those won't be handed back to you before the exam, so if you want to have that, I'll post solutions on Monday, but if you want to have your homework, I would recommend making a copy of that or something before you turn it in. That's if you want. Okay, excuse me. Well, we are going to resume our discussion of Chapter 4 today, kind of forging ahead with Section 4.3. Remember we talked about a new distribution, the normal distribution. We introduced this on Wednesday and kind of saw that it's you'll see this a lot. It's very prevalent in all of statistics for some reasons that we'll see later. But anyway, we're going through our usual setup of looking at its density function, probability density function, thinking about how to calculate probabilities for various values. Talked about the expected value and the variance. And then we introduced this capital letter Z, which is going to be our standard normal random variable, which is kind of what we'll use to calculate probabilities about normal distributions in general. And then, of course, remember our notation is x is a normal random variable with mean mu and sigma squared. We'll use x with a tilde and then a capital N, and then mu and sigma squared, and that's going to be our notation for a normal distribution. And there's just a kind of a refresher of how we can use this formula right here, the x minus mu over sigma, to transform any normal random variable to a standard normal random variable, and then calculate probabilities on that scale. That's going to be an equivalent way of doing it. So if I want the probability that any normal random variable is between a and b, I can apply that transformation to everything inside the probability statement, and then use the table like we looked at briefly on Wednesday as well. We'll do a few more examples of this today. And yes, so just to emphasize that any normal random variable you can calculate probabilities for any normal random variable using this standard normal random variable trick that we're talking about here. All right, so we started and got through part of this example on Wednesday. This is page 11 of your Chapter 4 notes. We were looking at mopeds and maximum moped speed, and we were told that that has a normal distribution with mean 46.8 and standard deviation 1.75. So again, we would write if x is the maximum speed, we would write x is distributed as a normal random variable with mean 46.8 and variance 1.75 squared. So just the problem gives you the standard deviation, and then we'll write down what the variance is there. So this is nothing new, but we didn't quite get to part C of this question. So we wanted to, the last example I want to give you for this question is, what's the probability that the maximum speed differs from the mean by at most 1.5 standard deviations? So again, remember x has mean 46.8, standard deviation 1.75. So what's the probability that we want here involving x? Probability that x is at most 1.5 standard deviations away from the mean. So what range of values will I want to consider?
Plus or minus 1.5 sigma.
Yes, exactly. So I want to go out from the mean 1.5 standard deviations, and then include the values in between that. So I want the x to be between two numbers. The lower bound here is its mean minus 1.5 standard deviations. So 46.8 minus. Sorry, let me start this over. Give myself a little more space. So I want to go from 46.8 minus 1.5 standard deviations. So 1.5 times standard deviation, which is 1.75. And I want to go all the way up to 1.5 standard deviations above the mean. So that's 46.8 plus 1.5 times 1.75. Which is the same as if I simplify that out. That's the probability that x is between 44.175 and 49.425. Okay, so now if I, again, we don't have a table or anything for just any normal random variable, so we want to transform this down to a standard normal random variable, which means this is the same as subtracting off the mean, 44.175 minus the mean divided by the standard deviation. Sorry. Do the same thing for each part of this. Sorry, I ran out of space a little bit over there. And again, the mean is 46.8, the standard deviation is 1.75, and then what I know is that this thing is a standard normal random variable. So x minus mu over sigma, that's a z. So this is the same as the probability that z is between, again, you could guess, negative 1.5 and positive 1.5. And now, since we want to use the CDF to find what this number is, we can use our usual trick. This is equal to probability that z is less than 1.5, and then subtract off the probability that z is less than negative 1.5. If you can imagine the picture of what this normal curve looks like, that picture should make sense. Yeah.
Just notational side, when you're defining a CDF and you're going from a PDF, why do you use circulated less than or greater than, right?
Okay, so again, what I should have here is that what you're thinking?
Well, just when you define it on the solutions to one of the problems, when you went from a PDF to a CDF, instead of in the PDF it was like less than or equal to some value, but in the CDF it was less than 2, for example. Is that really important, or?
Well, I guess I'm not sure the exact example you're talking about. The question was sort of just like when you're talking about probability density functions and or CDFs for continuous random variables, the endpoints, you don't have to be as careful about them, about whether they're included or they're not, because again, remember the probability of a continuous random variable being exactly equal to any number is 0. So that doesn't change the calculations, I guess. So I'll try to be very careful about that, but
well, I just don't want to lose points.
Yeah. So you won't lose points is the point with a continuous random variable here. Discrete, obviously that's a big deal. The endpoints are very important, but for continuous, you can be a little less careful about that. Yeah. So again, that's why I can leave the less than or equal to on there, and it doesn't change. So again, if I wanted to be exact, I should probably put just a less than sign there in that last probability, but because I want to use the CDF, I'm going to leave the less than or equal to there. So again, this is the standard normal random variable, so we have some sort of special notation. Remember, this is a capital phi of 1.5 minus capital phi of negative 1.5. That's why I'm leaving that inequality there. That capital phi is just our notation for the standard normal CDF. And then to actually figure out what those two numbers are, we can revisit our table, and I think I do have the correct parts of it up here today. So remember, this table gives me the probability that a standard normal is less than or equal to some small value z. And then I can take the value that I'm interested in, find it on the table, and trace it over to figure out what probability I want here. So again, the first one I want is 1.5, so I can find, can trace down here to the 1.5 row. And again, I want 1.50, so I can look at the first column here. The probability that I want is right there, 0.9332. So this is 0.9332 minus something else. So then if I want to check out negative 1.5, I can look at a different part of my table. I can look at the tenths column and find the right one that I want. So again, I want the negative 1.5 row. I just want 1.50, so again I can look at the first column here and pick out 0.0668. And then that is going to give you 0.888664. Yes, sir.
Can you just read the problem and jump to that last line and solve it?
Read the problem.
Do we have to do all the intermediate stuff?
Oh, yes. So if you I'm filling in a lot of the details just to kind of help us see where we're going here. But if you can jump, well, I mean maybe since we were talking about plus or minus 1 standard deviation, maybe you could have jumped right there. That's okay. But again, I want the probability that the maximum speed, or x, differs from its mean by at most 1.5 standard deviations. So I want to take whatever the mean is. I want to go down 1.5 standard deviations. I want to go up 1.5 standard deviations. So the picture to keep in mind here is this is my normal distribution. Here's the mean. Here's the mean plus sigma. Here's the mean minus sigma. And I want to know the probability that x is between those two values. So I'm just calculating using the mean and the standard deviation. Sorry, this should be 1.5 sigma and plus 1.5 sigma. Sorry about that. So then I'm just using the specific mean and standard deviation that I know from this problem. I'm figuring out what those endpoints are. and then I standardize it to get to the standard normal random variable, so I can use the table to find the probabilities, and then I actually go find what those probabilities are. Yeah.
So does that mean that you want us to use, like, I guess, scores to convert it to Z?
Yeah.
Like, for example, if the calculator can do it with the mean given.
Yeah, so if you have used your calculator, you'll know that it can also do normal PDF is in there too, and CDF. If you want to do it that way, that's fine. So just again, if you're going to use your calculator on a homework or exam, just kind of write out clearly I used my calculator to find this probability.
Like write normal CDF.
Yeah.
Mean 46.8.
Yep.
Okay.
Yep, that works totally fine. Okay, well, so maybe I'll just before we leave this problem behind, maybe I'll just point out quickly that there's a slight shortcut here. So if this is a Z, I'm going up 1.5 standard deviations and down 1.5 standard deviations. Remember that this thing is symmetric. So what do I know about those tail probabilities? They're the same thing, right? So if you take, again, you'll notice to find the area in between here, we took probably being less than 1.5, which was 0.933, whatever that was, and then we subtracted off this tail probability. But you could have just subtracted that tail probability off of 1 twice, and that would be the same thing. So there's a number of ways to get to these answers. Use your favorite strategy. It doesn't really matter to me. But just to point out that there are different ways. And maybe, again, so what we found, so this 0.60668, that's equal to 1 minus the other probability we found, 0.99332. So there's that there's that relationship going on there as well. That's just an additional thing to think about there. Okay, well, let's do one more example. I'll move through this one a little more quickly. This combines a few things that we've seen before. So now we're from this article. We guessed that the normal that for the contents of a certain type of jar, we know that the contents of that jar are going to be normally distributed with mean 137.2 ounces and standard deviation 1.6 ounces. So that's kind of what we're going to say. That's what the distribution of the fill of these jars is. And the stated content, what it says on the jar, is that it contains 135 ounces. So what's the probability that a single jar contains more than what's the stated contents? So again, let's set up some notation. Let's let X, you know what, let's use Y. Let's mix it up a little bit. Let's let Y equal the total contents of the jar. And what we're saying here is that Y has a normal distribution with mean 137.2 and standard deviation 1.6 squared. Variance 1.6 squared, sorry. And we want to know the probability that that a single jar contains more than the stated contents, which is 135. So what's the probability statement that I want involving Y? And everybody said greater than 135, exactly. I want to know the probability that it's more than contains more than the stated contents. Again, so to figure this out, I can standardize. We want to do this by hand. Take Y minus its mean, which is 137.2, divide by its standard deviation, 1.6. Do the same thing for 135. 137.2 divided by 1.6. And so that means I have a standard normal random variable. Z is bigger than, I want to see that's bigger than negative 1.38, which again we can find using 1 minus probability that's less than 1.38. So sort of the standard trick there. And to actually figure out what that probability is, we'll again jump back to the table. So if I want negative 1.38, I need to be in the negative 1.3 row. So that's right here. And then which column do I want to be in? So second to last, yeah, so the 0.08 column. So I can just trace this one over. And the probability that less than negative 1.38 is 0.0838. So this is 1 minus 0.0838 or 0.9162. Okay, so the probability that the jar contains more than its stated contents is pretty good, right? Pretty good chance that it contains more than what it actually says. This is probably not a very realistic manufacturing example, but anyway. Okay, so kind of connecting this back to something that we've seen before. So suppose I take 10 randomly selected jars. What's the probability that at least 8 of them contain more than the stated contents? So what distribution are you going to want to use, or how would you attack this problem? Yes, absolutely, binomial distribution. So let's let's go back to x, I guess. Let's let x equal the number of jars out of 10 with that are overfilled, I guess, let's say. And then x is going to be a binomial random variable. Very good. With 10 trials. And then what's my success probability here? Exactly, the thing that we just found. So the probability that the jar is overfilled is 0.9162. Very nice. So then if we want the probability that at least 8 contain more than the stated contents, that's probably that x is what? At least 8, translate that into an inequality for me. Greater than or equal to 8, right? I want x to be at least 8. So again, you can use your favorite trick for finding this. I'm going to use the table. This is 1 minus the probability that x is less than or equal to 7, which we can then find that from, you can use your calculator, or we could actually calculate that out. I'm just going to tell you this is 1 minus 0.0451, which is 0.9549. So I'm skipping over the details of actually calculating that, but I think you guys are getting practiced up with that enough by now. Is that okay with everybody, what we're doing here? Kind of making that connection back to the binomial distribution? Okay. Last question, something a little different again. So assuming that the mean... Yeah, sorry, Kevin.
Would you be able to do it, how would you do it differently in regards to acknowledging 8 trials that have success and 2 that fail and 9 that are successful and 1 that fails?
How would you calculate it directly?
Yeah.
Well, yeah, so this up here, again, that's, if you think about the individual probabilities, that's x equals 8, 9, or 10, right? So x equals 8, plus probability that x equals 9.
So that's just multiplication rule, right? Summing it up.
Just the multiplication rule?
Success to the 8th.
Oh, sorry, yeah, right. So now I can use my binomial probability mass function, right? So, for example, probability that x is 8, well, that's 10 choose 8 times p, which is my success probability. So here that's 0.9162 to the 8th times 1 minus 0.9162 to the 10 minus 8, so it's squared. And then do the same thing for those other ones. Yeah, so that would be an equivalent way of getting that same answer. It's a good question. Other questions you guys can think of? Okay. Okay, so last part of this problem here, if we assume that the mean stays the same, so the mean is still 137.2, and suppose that we had control over the standard deviation, which is often the case in a manufacturing setting, what would that standard deviation have to be so that 95% of all jars contain more than the stated contents? So again, I have my normal distribution here. This is y centered at 137.2. And I want to find some value here, or this is going to be 135, I guess. That's the stated contents. And I want to know what my standard deviation is such that this is 95%. Okay, so I want to find what my standard deviation is there such that I get this property. So let's first think about it on the z scale. So let's pretend there's a secondary axis down here, centered at 0. What z-score? Start to think about what z-score gives me a probability of 0.95 of being larger than that. So the probability that z is bigger than some value equals 0.95. I want to figure out what that is. So if I have 95% of the area above, how much area do I have below? 0.05, exactly right. I think I might have this on my table over here. Okay, so again, I want to look on my table now. So if I want that means this area down here is 0.05, and I'm switching to that scale just because that's what the table gives me. The table gives me area to the left. So if I want to know what z value gives me that probability, I need to now look inside the table and find something that's close to 0.05. So I can search around. And lo and behold, here I find two numbers that are both very close to 0.05. And so you can take your pick, or we can also take the average of those things too. That'll work just as well. So again, I want the probability of z to the probability of being less than that to be equal to 0.05, which tells me that z is going to be equal to negative 1. So I'm in the 1.6 row, and so negative 1.6, and then I'm going to put a 4.5 there. So you could use negative 1.64 or negative 1.65. Either of those would be fine. The difference is going to be pretty small here. So the critical value, the z value, such that probably being less than that is 0.05 is negative 1.645. So then I can now fill in this statement here. So if z has to be bigger than negative 1.645 for that probability to be equal to 0.95. So now this number down here we know is 1.645. Okay, so we're not quite there. So again, we know that z equals x minus, well, let's use our y again. Z equals y minus mu divided by sigma. So I know what z is. I know what y is. I know what mu is. So I can now use this to solve for sigma. So z is negative 1.645. Y, I still want to use the 135 that we used before. The mean is 137.2. And now I'm dividing by some new standard deviation there. And you can solve that one backwards to get that sigma is equal to 1.337. This is getting a little more involved as we go on here. Is that okay with everybody? Any questions you can think of? Okay. Very good. Okay, so before we leave the normal, I had that on there twice. That almost threw me off. All right, so before we leave the normal distribution, I want to talk about one more approximation. We looked at something like this back in Chapter 3 with the Poisson approximation to the binomial. There's also a normal approximation to the binomial. So the binomial becomes sort of cumbersome when you have large values of n because you have factorials and combinations and all those things. So whereas the Poisson approximation was a little bit less helpful maybe, or might have seemed that way, this is actually going to make your life a lot more simple, something that is actually very useful. So if x is a binomial random variable with n trials and some success probability p, so as long as the binomial probability histogram or probability mass function is not too skewed, then we know that x has approximately a normal distribution, and it's the approximate normal distribution has mean exactly what you would think it is. So mean that's the same as the binomial mean, and variance that's the same as the binomial variance. So that's exactly what you would expect. So then kind of writing it out explicitly, the probability for a binomial random variable x, the probability that it's less than or equal to some value is going to be approximately equal to the normal CDF. Again, you could think about this is almost in here. This is almost an x minus mu over sigma. That's almost what we have going on there, right? We're taking an x here, we're subtracting off its mean, and we're dividing by its standard deviation. So that should look familiar to you. But then there's a few details to talk about in here. So the first thing that it says, as long as it's not too skewed, then it has this. Then this approximation is good. And we also have this 0.5 floating around in there. You might wonder what that is. So not too skewed. I mean that this down here. So I want to make sure that n times p is at least 10, and n times 1 minus p is bigger than 10 as well. So that will ensure that my binomial distribution is not too skewed in one direction or the other. So before you use this approximation, you want to make sure. So this is sort of your check. Can I use the approximation? And there's your what you need to do. That's sort of a good rule to make sure that this is an okay thing to do. Okay, so we still need to talk about what this 0.5 thing going on here is. So in here I put there's a picture in your notes as well. I've sort of superimposed a histogram, which is representing the this is sort of the same thing as a probability mass function, kind of representing what that would look like if you have blocks instead of just a line for each probability. And this is for n equals 20 and p equals 0.6. And then I've overlaid a normal distribution on top of that with mean n times p. So here's n times p, and variance n times p times 1 minus p. And you can see that it's it's our favorite proof, right? The proof by looking at it. I can tell that it looks pretty good, right? It matches up pretty closely with the shape of that histogram. The normal curve's pretty good there. So this picture hopefully also helps you see why we need this 0.5. So it's called the continuity correction, and that just means we're going from the binomial is a discrete random variable, and we're going to a continuous random variable. So if I'm looking at the probability of being equal to 10 here, if I'm with the probability of being less than 10, there's some area up here and some area in there that I'm leaving out and that I'm adding in. So the 0.5 kind of helps me correct for that error that I incur by approximating a discrete thing with a continuous random variable. So yes, so that's why we have the 0.5 in there. Okay, so let's do an example to apply this thing, see how this works. So here, suppose that we're talking about seat belts. So suppose only 75%. I won't ask you in here who wears their seat belt because we all do, right? But in some theoretical state, we have 75% of drivers wear their seat belt. We have a random sample of 500 drivers, and we want to know some probabilities. So first of all, what's the probability that between 300 and 400 inclusive of the drivers in the sample regularly wear a seat belt? So if I let X be the number who wear a seatbelt of the 500, what distribution does X have here? Maybe kind of obvious, but it's good practice. What distribution is X going to have here? Say again? Yes. So that's the probability we're going to look for. But before we get there, just maybe wanted to note that X is a binomial random variable with 500 trials and success probability 0.75. So just remember that. And then yes, exactly. We want the probability that X is between 360 and 400. And if you have your calculator, I would actually encourage you to try to figure out what that number is using your calculator. And your calculator can obviously do it, but you'll notice that it does take just a second. It takes just a second for it to do the calculation. Again, it's because because n is really big here, so that causes a little bit of a slowdown. So this approximation can kind of speed things up. Anyway, sort of the usual strategy here is that this is equal to the probability that X is less than or equal to 400 minus the probability that X is less than or equal to 359. Okay, so again, we could, up until this point, we haven't done anything differently. But again, if we want to use our approximation, we can note that since n times p, which is 375, that's bigger than 10 on most days anyway, and n times 1 minus p, which is 125, is also bigger than 10. Then we can use our approximation here. So let me maybe come down over here. So because that's the case, we can say that X is approximately distributed as a normal random variable with mean 0.75 times 500, and then 0.75 times 0.25 times 500. So it's normal with mean 375 and variance 93.75. So because n times p is bigger than 10 and n times 1 minus p is bigger than 10, we know this approximation is going to be pretty good. So then to figure out this, so this probability that we want is approximately equal to the standard normal probability of 400. We're going to add on 0.5 and then subtract off the mean, so minus 375 divided by 93.7, sorry, the square root of 93.75. And then similarly, we can do the standard normal CDF of 359 plus a half minus the mean 375 divided by the standard deviation, the square root of 93.75. So this is the standard normal CDF at 2.63 minus negative 1.60. Working out that calculation there. And then I'll let you practice using the table. That would be, give the probabilities it gives us there is 0.9957 minus 0.0548 or 0.9409. So did anybody do that? Did anyone actually calculate the binomial probability in their calculator? 0.9403. So we're pretty close there. Off by 6 ten-thousandths. Not bad. Questions or comments you guys think of on this? Let's do one more of these. And there's all my extra space. So same question. So what's the probability that fewer than 400 of these in the sample regularly wear a seatbelt? Well, this is very similar to what we just did. So that's the probability that x is what? Less than or equal to 399? Yeah. So we want the probability that x is less than 400, which again, yes, is equal to the probability that x is less than or equal to 399. Again, the same checks hold from the previous part, so this is approximately equal to the normal CDF of add on the 0.5, subtract off the mean, and divide by standard deviation, square root of 93.75. Which is, if you do the calculations, 2.53, which is equal to 0.9943. So again, I'm skipping over the step of actually using the table. Do I have the table in here? No, I don't. Maybe let's go, well, I'll let you guys double check that is indeed the correct probability. All right, that brings us to the end of 4.3. Any questions you guys can think of on the normal distribution? So I guess it's just, I guess I would just encourage you to get comfortable, and maybe you're already feeling fine with using the table. Again, it's kind of a clunky thing. If you have your calculator, that's fine too. But the table can be good for finding if you need to find a percentile or something. That's kind of the best way to do it. Yeah.
On the exam, we're going to give it a table, right?
Absolutely, yeah. So on the exam, you would, again, this material will not be on the exam, but if it was, or the next exam when it is, a table will be included. Absolutely, yeah. No need to memorize the table. I'm not going to do that to you. Okay. All right, well, forging ahead to section 4.4, the last topic we'll look at here in chapter 4. We're We're going to talk about a few more continuous distributions before we move on. And the next one we're going to talk about is this thing called the gamma distribution. And so we talked about the normal distribution is often used for things that are measured because, again, it has the range goes from negative infinity to positive infinity, so you'd never have to worry about having sort of like an invalid value or something. The gamma distributions are used to describe non-negative and skewed distributions. So for this, the values of x are going to only be positive, and it's going to be skewed. So we'll look at some pictures in a minute here, but that's kind of the situation that we're in now. So it's kind of very different from the normal, which has sort of the range is the entire real line. Here we're only looking at positive numbers. So there in your notes, I guess there's some examples of things that only take on non-negative values. So we have things like income, sort of lifetime of a light bulb or some component, some response time. So if your response time until you can, so you're looking at something and seeing how long it takes you to respond. Can anybody think of other things that are non-negative quantities that we might use a skewed distribution to model?
Skewed is non-symmetric.
Yes, so skewed is, well, yeah, that's a good question. So skewed is going to look something like this. So it's kind of it's not symmetric. It's going to kind of tail off when you get to really large values. So house prices is another thing that's always skewed, right? Most houses kind of cost in a certain range, and then there's a few really expensive ones. Any other number of shirts you own? That's a great one, right? Most of us have sort of a certain range, and maybe some people have a lot of shirts, right? Yeah. Yeah.
The scores on a hard exam you want.
The scores on a difficult exam. Yeah, that you could think about it that way. They're all positive, right? Maybe most are going to be kind of bad. Hopefully, it's not. If it's a really difficult exam, most of the scores might be kind of bad, but a few people did really well. Or it could be skewed. A really easy exam would be skewed in the other direction, right? Most of the scores are large and it kind of trails off. Anyway, sort of getting ahead of ourselves here a little bit, but I just wanted to get you guys thinking about what types of things. You think about what are our examples going to be about here in this section. Okay, so before we get into looking at the PDF for a gamma distribution, need to introduce some notation here. This thing called the gamma function. So this here is that's a capital letter gamma there. And it's defined by that really messy integral, which is not something that you would want to try to calculate, but something that you could calculate. So this is going to be one part of the PDF is kind of where we're going here, and just some properties that of this gamma function. For any value alpha bigger than 1, it sort of has this recursive property. So gamma of alpha equals alpha minus 1 times gamma of alpha minus 1. And if you're feeling extra bold today, you could figure this out. This is by integration by parts. So everyone in here is very strong in their integration by parts, right? If you wanted to, that's how you would establish that is true. So we're not actually going to go through that, but that's what you could do. Sort of a simple case is if alpha up there is an integer. So if we have an integer valued thing in there, that's actually just the same as, it's very similar to the factorial. So gamma of n is equal to n minus 1 factorial. And then sort of you might think, why am I putting this up here? But that's just kind of a very strange property. One of the cool math facts, I think, that the gamma function at a half is actually the square root of pi. So you kind of have that. It's strangely exact there, I always think. Anyway, so the only reason I'm showing you this gamma function here is because it shows up in our PDF for a gamma random variable. So A continuous random variable that has a gamma distribution has a PDF that looks like this. So it's we're getting more and more messy here. 1 over, and then it involves two parameters, alpha and beta, both of which have to be positive. But it's 1 over the gamma function evaluated at alpha times beta to the alpha, and then the sort of the meat of the distribution is there involving x to the alpha minus 1 times e to the negative x over beta. And then the important thing here is that x has to be positive. And let me make a little change here. This should actually be strictly greater than 0. If you have a really small alpha, you'll get some problems if you try to plug 0 in there. And then our notation down here is that x is distributed as a gamma random variable with mean alpha, parameters alpha, and beta. And then so we won't worry too much about the form of the PDF there. But then again, I just wanted to kind of show you a few examples of what these distributions look like. So the normal curves are all sort of symmetric and bell-shaped. The gamma distributions can have very different shape depending on what the parameters are. So there's just a few examples. It's a more colorful picture than what's in your notes. So in the normal distribution, we had a very, very nice interpretation of what mu and sigma squared were, right? Those were our two parameters there. Mu is obviously the mean, sigma squared was the variance. So what does alpha and beta mean here? Well, it's not quite as clear, but they do have a name which sort of give you an idea of kind of what they're doing here. So alpha is called the shape parameter, and that's because it kind of controls the shape of this distribution. So when alpha is less than or equal to 1, the PDF is going to be strictly decreasing. So that's the green and the blue curve. So they're always decreasing. They start up really high and they're always decreasing. Whereas if alpha is bigger than 1, then you kind of it rises first and then it tails off. So that's controlling kind of what shape this thing looks like. And in this picture, I've set beta equal to 1. And beta is called the scale parameter, and that just kind of this is kind of like a variance parameter. You think about it that way, is that it's kind of tell you how stretched out or how compressed in the PDF is in the x direction. So you can see as beta gets larger here, going from 0.5 to 2 to 4 to 8, this thing gets more spread out. So again, we won't often talk about a direct interpretation of these parameters, but that's kind of what they're doing in the density function here. And maybe just to finish off, tell you some useful properties of the gamma distribution. So I'm not going to derive these, but you could. The expected value of a gamma random variable is again involves the parameters alpha and beta. It's alpha times beta. And then the variance is going to be alpha times beta squared. So once again, I have run out of class time before we do an example of this thing. But before I let you go, any questions or comments you guys can think of on any of this stuff? Okay, well, we'll look at a few examples. I do have your homework too up here, so please feel free to come on up and grab it. Otherwise, you guys have a great weekend, and we'll see you on Monday.